Okay, I think we can get started. Thanks again to everyone for joining us today for our webinar, Detecting Fraud and AML Violations in Real Time. My name is Emily, and I'm helping moderate the webinar today. We're going to start out with a few housekeeping items. So if we can go to the next slide. Just as you know, attendees are muted, and we're going to have the Q&A at the end of the webinar today. But you can go ahead and ask questions at any time using the Q&A tab in your Zoom interface here. And the webinar is also being recorded. If you can't stay for the entire webinar, we are going to send that out later today. The link to the presentation and slides will also be emailed. So we're going to start out by introducing our speakers today. We have Victor Lee and Gaurav Deshpande. I'm going to let Gaurav take over from here.
Hi, Victor. Would you like to introduce yourself briefly, and then we can jump into the first part of the presentation?
Sure. Hi, this is Victor Lee, Director of Product Management at TigerGraph. This is my third webinar. Some of you may have met me before, and I'm really pleased to be joined today with our VP of Marketing, Gaurav Deshpande, and he's going to start off, so I'm going to hand it back to him.
Thank you, Victor. It's great to have you all here. I'm Gaurav Deshpande. I run marketing at TigerGraph. We have a packed house today, and I'm excited. We have executives from several banks, we have insurance companies, we have e-commerce and payment providers, and we have telecom providers from United States, Europe, and all the way to Australia. So it's an exciting day. Thank you for joining us. We also have healthcare providers in the audience today. I would like to thank all of you for taking time out of your busy schedules and joining us today. I have been designing solutions for enterprise software for about 22 years now. I have focused on telecommunications, e-commerce, and banking for the last 15 years of my career, and I've been focused on big data. I'm really excited to share with you today best practices from China Mobile, from Alipay, from Uber, from a host of other clients that have used TigerGraph to detect and prevent fraud and money laundering activities in real time. Let's take a brief look at the agenda for today. So we'll briefly touch upon impact of fraud and money laundering on various industries. We will look at the traditional approach for handling these issues and why the current approach isn't working well as fraudsters and money launderers get more and more sophisticated. Next, we'll look at a new approach based on real-time analysis of data called real-time deep link analytics. This approach improves the accuracy of fraud prevention, and it helps you find money launderers faster with more accuracy. Lastly, we'll talk about three ways that you can get started now with your journey to reducing fraud and money laundering violations as a part of your organization. Fraud is a big problem, so I found a few examples here for us to look at in terms of the impact of fraud across multiple industries. The first quote there from Experian, it's a credit rating agency in the United States. They do their annual survey every year, and they did one in January of this year that spans thousands of executives across multiple industries. They found that 63% of businesses, that's 2 out of 3, businesses continue to experience same or more fraud in the last 12 months. Now, as we look at increase in e-commerce and online payments, CNBC estimated that the cost to consumer just for online fraud alone is $16 billion, and that's the tip of the iceberg. For every $1 that costs consumers in fraud, the banks and the merchants end up paying $1.40. So total of $2.40 in charges for every dollar of fraud. That is in administrative costs and penalties. So the problem is much bigger, and we're just talking about online fraud. Coming to the bottom of this chart, let's talk about telecommunications. GSMA is an organization that those in telecom are very familiar with, one of the largest organizations that has telcos who's who across the globe. They estimated in 2016 that $300 billion was the total global loss for uncollected revenue and fraud. And that has gone up in 2017. So that's the size of the fraud problem. Now let's look at money laundering for a moment. It even exceeds the size of the problem for the fraud. First figure there, $342 billion. I want you to think about that for a moment. That is the total amount of fines that United States and European Union regulators alone. I'm not talking about Japan, I'm not talking about China, I'm not talking about India. Those regulators have additional fines, but just United States and European Union, they have fined $342 billion for banks. And a large percentage of that has been related to money laundering violations. So $342 billion is a large number. Let's come to a specific example in the middle of that chart. It's a U.S. bank that has been charged $613 million just 2 months back for lax money laundering control. So finding money launderers is a strategic priority, and it's a mission critical priority for every bank that we speak with. Payment providers, e-commerce, everybody, but especially the banks have been hugely affected by this. Now that we know the size of the problem, let's look at how well we are doing at detecting these things. The quote at the bottom is a quote from Bloomberg, and it was just published about last week. Total of 5% out of all the suspicious transactions that the firms find, about 5% are reported back to the authorities. Out of that 5%, just 10% out of that, so 0.5% of the total suspicious activities, transactions are actually investigated, which means money launderers out there are having a great time getting through the system, and that's not for the lack of trying. There are, by any estimates, major banks have tens of thousands of people that are working on fraud and money laundering. Adding more people to the problem is not going to solve the problem because the traditional approach is broken. So I'm going to take a moment to walk you through what the traditional approach looks like and why it's where the deficiencies are. So we have data on the left here. This is the flowchart that shows how the traditionally fraud and money laundering is detected in current organizations. We have data on the left-hand side with all of the transactions. The payments, the e-commerce orders, the calls, if you're talking about telecom industry, all of those are getting into fraud analytics solution. We also have what is called master data about customers, accounts, merchants. If you're talking about ride-sharing companies, drivers, for example. It's also the data about devices and locations that are generating all of these transactions. All of that data is typically loaded into a fraud analytics solution. It has its own rules engine, or it typically integrates, in some cases, with a third-party rules engine. Fraud analysts then work on creating rules for detecting fraud, for detecting money laundering violations, and then fraud analytics tool will process all of this information in batch mode, find suspicious activities, and that's passed on to what are called the fraud or money laundering investigators. Now, as the investigators typically need more information, they'll come back and query the fraud system for more information, and then they will determine a final set of transactions that are reported to the authorities in case of money laundering, called SAR, Suspicious Activity Report, right? That's the end-to-end process. Now, what many banks and e-commerce providers are also starting to do, payment providers are starting to do, is to feed those suspicious transactions, the final set, into a machine learning solution. The idea is AI machine learning solution will help us understand these patterns of fraud and money laundering, and then they'll start to detect those with higher accuracy as time goes by. All of that is a brilliant idea, an excellent idea, but then let's look at why it hasn't been working well. So the reason why current approach hasn't been working well, because it's typically focused on attributes or features or fields of individual nodes, like a phone, like a payment, or a user account in question. So for example, in order to find, let's take an example of the phone scam, because that's the first scam we're going to talk about. In order to find all phones that are involved in a scam, typically if you look at features of phones calling history, like frequency and duration of one-directional calls, because we know that scamsters would get a prepaid SIM card, a phone, and then start calling people. And many of those are one-directional calls, and they are short calls, because when somebody receives a call from somebody that they don't know and they suspect something, they'll hang up, right? So that's the type of features you're looking for. For the payment transactions that are involved in money laundering, for example, you're looking at size and frequency of payment transactions and looking at those. So this is a simplistic, that's what the rules are based on. The rules are also based on looking at one level of differentiation. So they will typically look at how a particular phone is calling other phones, and maybe how that phone is calling other phones. 2 or 3 hops in the network is what you're looking at, simplistic rules based on that. The problem is the fraudsters are getting more sophisticated. And if you see on the right-hand side, a single directional call, like you have a lot of one-directional calls and you have a frequency of those calls, it doesn't necessarily mean that this particular phone belongs to a scamster. It can also belong to somebody who is selling ads, somebody who is selling products and services over the phone. So it could be an executive, sales executive that is selling that. It could also mean that somebody who is harassing somebody else, which is a cause for concern. But when you're specifically trying to find people who are trying to do scamming over the phone, you end up with a lot of what are called false positives. So that's the reason why the current approach is breaking down, is because it's typically based on calling patterns in case of phone scam for a single individual subscriber. Now, as you're looking at that, you're looking at feeding that same data with the false positives into a machine learning tool. You end up with garbage in, garbage out. Essentially, a machine learning tool with the poor training data that you're feeding into it will not be able to improve its accuracy in terms of predicting a phone scam or in terms of predicting money laundering. And that's the reason why 3 out of 4 projects that are trying to do machine learning for fraud or AML fail because of poor training data. Training data that is features that are not highly correlated with the final fraud or money laundering activity. So with that, we started talking a bit about phone scam. Let me talk a little bit about that here. One of the most simplest and effective scams is a phone-based scam. For all the sophistication that blockchain has and all the security that it provides, bulk of customers who have been losing Bitcoin to fraudsters have been through phone-based scams. Typically, a fraudster or a scamster calls the person owning a Bitcoin account and manages to get enough personal information about them to be able to log into their Bitcoin account and steal the coins. That's the reason why phone-based scam continued to be a factor even in this day and age. So now with that, let's look at how a solution that is focused on network of activities, like TigerGraph, that goes beyond just individual calling patterns, detects the fraud. On the left-hand side, you have the good phone, and the right-hand side, you have the bad phone. So a TigerGraph essentially identifies features by analyzing relationship among phones to identify what's a good phone, right, belonging to a good customer, regular customer, and what's a bad phone, what's likely to be involved in a scam. Now look at the left-hand side of this chart. Customers with a good phone calls other customers, and majority of those calls are returned, indicating that there's a familiarity or a trusted relationship. A good phone also regularly calls a set of phones every week or month, and this group of phones is fairly stable. So you see that stable group on the left-hand side, on the top right-hand side of the good phone. That's a stable group, meaning that they actually have relationships and they call them regularly. You also see that there's a lot of many in-group connections. So the good phone 1 is calling phone 5, phone 4, and phone 4 or 5 are calling each other. Same thing with phone 5 and 6. So there are stable groups that they are calling with, and then there are in-group relationships. There's another important thing called three-step friend connection. You'll see that on the left-hand side in the good phone 1 calls phone 2 also calls phone 11, and phone 11 calls phone 3. And then there is a completed loop of phone 1 calling phone 3. So that is a three-step friend connection. So it's like me calling my friend, that friend calls another friend, and I'm calling the other friend as well. That is the characteristics of the good phone. Now you come to the right-hand side and you will see all the things that are wrong with that one, right? On the bad phone side, you'll see that you see those X's. That means there are many rejected calls. So a lot of the times this bad phone is calling other subscribers and they are rejecting the calls. You'll also see that on the right-hand side, the bad phone has an empty stable group. What does that mean? That means they are not calling somebody a set of calls, set of people regularly on a weekly or on a monthly basis or on a daily basis. That basically means that they have no relationships, long-term social relationships inside the organization. All of those flags put together become the cause for concern. You'll see on the bottom left-hand side of the bad phone, there is no three-friend connection. So phone 1 is calling phone 2, but there is no connection back to phone 4. the loop is not completed. And that also indicates the fact that this is somebody who is just calling people randomly without getting callbacks and doesn't have established closed loop relationships. This is how TigerGraph or a graph-based solution is different, because it goes not just one level of relationship, 2, 3, 4 hops throughout the network to find good actors and confirm bad actors. So these features that you saw have a really, really high correlation ultimately with the bad actors, and you're able to find those. Now, on the next chart, you'll see that customer example from China Mobile. They have about 500 million phones that are part of the network. They have 10 billion calls that are all loaded up inside the TigerGraph network graph database. And then there are thousands of new calls per second that are getting updated, that are updating this particular network. So this is not a static batch-based system. This is a real-time update system. All of this is generating about 118 new features, new attributes that are based on network analysis. These are attributes that are highly correlated with indicating what's a good phone and what's a bad phone. And when you have the activities highly correlated with a good phone and a bad phone, they are all pumped into the machine learning solution every 2 hours, making their machine learning solution that much more accurate for detecting fraudulent activities. With that, I'm going to hand it back to my colleague, Victor Lee, who's going to talk a little bit about evolution of the graph technology. Victor?
Great, thank you, Gaurav. So as the phone scam situation that Gaurav was just presenting shows, in order to process that, we had billions of phone call events, we had hundreds of features, we had thousands of calls coming in per second. So we needed the scalability and speed to handle all that. And that's required a new generation of graph technology. So the graph approach is a very powerful fit for this type of fraud, fraud detection and fighting fraud, but you still need the right type of technology. So I'll give you a little background on how graph technology has evolved. The first generation was basically demonstration of principle, the first generation of real products. And so we were able to store data as a graph, and importantly to also visualize it, because the visual aspect, it really helps communicate to people what the graph is doing. In this first generation, there wasn't a lot of emphasis yet on parallel performance. There wasn't thought about scaling out to multiple machines. So things like loading speed were not of first concern. So a little later, when NoSQL came along, then we got a new generation of graph databases. And so these were built on top of the NoSQL stores, such as Apache Cassandra or Hadoop. And so they now can scale out better. But the drawback is you now have a graph application or abstraction built on top of a different data structure. So you still don't necessarily have the native performance that you would have out of a natively built graph database. And also, while it can handle the scale, it's really designed in some cases for query speed and for a few hops, but it still is not necessarily performant for multi-hop queries and for high-speed real-time data loading. And so TigerGraph is the third generation as an example of the current and latest generation, and where it's really designed for massive data sets and to be performant with those massive data sets, and not just in query speed, but also in real-time updates. And those queries, as Gaurav mentioned, may need to be 3 or 5 hops deep, along with the enterprise features. So maybe in the next slide, you can sort of see the full set of enterprise features that TigerGraph offers. So starting from the left, as I mentioned, real-time multi-hop performance. And this comes about through our parallel design and really being designed as a native graph database. It's not built on some other type of technology. So it has the speed you need. Transactional. So phone calls are transactional inherently. There are new phone calls, they said, thousands coming in every second. The fraud attacks are coming in very quickly. They come and go. So your data set has to keep up. So it's very important that we're not looking at a pure analytics platform. We are looking at a platform that can do both transactional and analytical work. And of course, scalability. As we mentioned, we may have tens of billions, hundreds of billions. We have applications with trillions of relationships. So a modern solution needs to have that scale out ability. On the right side, deep link analytics. That's the term that we use to refer to queries that need to traverse 3 or more hops in the graph. Old style relational databases, in theory, the relational aspect can make connections from one data entity to another, but it's slow. And first generation graphs also, they can do this, but when the data set becomes large, there are performance problems. So TigerGraph, through its parallel design and other optimizations, is really designed to take all these deep analytics in stride. Just add another hop, no problem. And of course, as any enterprise data solution, you have to provide security and privacy and ease of deployment. So we won't focus on those today. We're going to focus on the fraud use cases. So if we can go on to the next slide, then we see that we've already looked at one type of fraud, phone scam. There are really many types, and there are as many types as there are different types of business. And we're just going to look at a couple more examples today. Credit card chargeback, advertising fraud or recommendation fraud, and then money laundering, which is a really special case and of great importance to the financial sector. So let's dive into credit card chargeback. I think this is something that all of us can relate to, because I would think all of us have credit cards. So if your credit card number gets stolen, it's a part of identity theft. That basically allows someone else to make purchases with the merchant believing it's you. They don't really know who is buying. They just know that this seems to be a good credit card, and as long as they can provide the right numbers, the right codes, they'll process the transaction. So the fraudster who has obtained your credit card number makes some purchases. Eventually, the card owner, or in some cases, the card issuer, realizes that this is actually fraudulent information and then cancels the credit card. So no future transactions can be made. But the fraudster has already made some purchases, has already obtained some goods and services, and just walks away with that. So that's a big problem. That's a huge problem in the industry. And who pays for it? So generally there is consumer protection. So the consumer generally either has zero or very low liability. Who eats the cost is both mostly the merchant and also the credit card issuer. It can cost them $2.40 for every face value dollar that is lost through this fraud. So this is a big problem. So what can we do? Well, through deep link analytics on a graph, what you can do is analyze the network to see. What you need to do is see how everything is connected, because any one transaction by itself shows relatively weak signals or not a really strong indicator that it's fraud. But it's when there's a pattern. Is this card being used multiple times in a short period of time to make purchases which are out of the usual pattern for this person? So that would identify the pattern around one card. But then, these fraud groups, they often have several cards. So can you draw a link between this card and a person and another card, or through a device that's being used to conduct the transactions? If these are online transactions, what IP address, what phone ID is being used? Graph technology allows you to make these 2, 3, 4, 5 level deep connections, and once it helps you to both detect a fraudulent pattern, and then once you have, to see what other cards might also be related, and to then, so that enables you to take action. The ability to import this data real time, to be adjusting your transactional analysis, as the transactions are occurring, growing your analytical capabilities in real time, so that you can catch the fraud in progress and minimize your losses. Because if you wait until, most of these fraudsters, they know their time is limited. They will try to do everything within a few hours, and then they will stop using that card. So you have to be very quick to capture this. So that's where this real-time deep link analytics can be a very powerful tool to combat credit card chargeback fraud. So another type is advertising or recommendation fraud. And this is something that's come about with the web and internet, and how we do advertising and how we do social recommendation on the web. So one thing, advertisers, they pay to have their ads show up, and they get, actually how much they pay depends on whether they get clicks or whether it seems that somebody viewed their ad. And also, there are different reward systems. Of course, you want your ad to be popular. So if you can show that you had many clicks or many views, that can be a benefit to one party. It's also a charge to the advertiser is having to pay for that. So you can promote yourself as popular. There are people who are trying to generate false popularity on Twitter, basically, coming up with fake followers. And on the other hand, you can attack a competitor by making them pay high advertising costs. But this is all done by robots, which are not real persons, but are sort of generating these clicks. Or it could be real persons who have managed control over hundreds of thousands of accounts and are just clicking. So that's one type of fraud. Another is, of course, we look at reviews to see, which product, which service should I use? Which restaurant is the best restaurant? Which phone is the best phone? So you look for product reviews, or you look to see, who is the most popular, who has the most followers. Again, there are fake reviews being written not by people who did not really purchase the product. And one way that the smart fraudsters are trying to disguise their activity is they hijack real accounts. So they may have access to your account and you have some real reviews, and they add in some additional reviews. Or they're camouflaging where they have an account and they write the paid reviews, but they mix in some legitimate reviews. This is a review that a real person, they really do like this product, and then they mix in the ones that they're paid to write. So that makes it harder to detect. So again, this is a serious problem in the industry. So if you map out what the fraudulent behavior looks like, what you see is a dense graph structure. You see one person who managed the fraudster at the bottom, who has some access to multiple user accounts, and then all those user accounts are densely linked to very focused on a few products that they've been paid to promote. either to write positive reviews of that product or to, follow this person on Twitter where the person is the product, the celebrity. So the trick is, if you can form a graph where you can map all this stuff out, then it becomes actually fairly straightforward to detect this. Again, there are some algorithms which are coming out just now to help filter out the camouflage. Those are being used, but you need the technology to be able to analyze the graph. So again, the data sizes are just getting bigger and bigger. So while the real-time capability may not be the most important here, but the scalability is important because of you may have millions of followers now. You may have, tens of thousands of product reviews, and these fraudsters are being very careful. They are trying to disguise their tracks. So you need the power to search out very large graphs and to filter out the noise and to try to detect this behavior, and then so you can filter it out. And lastly, we're going to talk about money laundering, and this is a topic that TigerGraph has, invested a lot of effort into. It's a serious problem. And we are helping a lot of companies to combat money laundering. So money laundering is basically transforming the profits from illegal activities and then passing it through with legitimate transactions. So the money that was in one pool over here, it gets transferred, it gets spent, and through those legitimate transactions, you've now sort of obscured the original source of the money. So there are several types of money laundering. One of the most common is structuring, where you basically break up your money you take your large amount of money and split it up into smaller cash deposits. Financial institutions are required to report large cash transactions, but if you split it up into small enough amounts, then those institutions may not report this transaction. It becomes harder to track. There's, of course, just simply smuggling the money in a suitcase or a crate with a lot of cash, mixing it in with cash-intensive businesses like restaurants, or round tripping, which is depositing it overseas and bringing it back as an investment. So there are many different types. So in general, we are working with institutions, including some payment vendors like Alipay that deal with billions of transactions every day to do real-time AML detection. So the first step is you need to build your data set. So, and this is where building what's called a customer 360 or a know your customer view is really important, and where graph databases are a great tool, because graph databases are great at integrating data from multiple sources and connecting them up. So you may have transactional data, you may have customer profile data, you may have social media data, you may have additional data which you've purchased from outside sources to integrate and enrich your data set. So then you assemble this all, and you need to be able to this is not a one-time task. You're constantly bringing in new data, so you need to be able to do these real-time updates. This creates this unified graph database. Then you have some sort of, based on past history of what turned out to be actual cases of money laundering, you can tag those events, and you now have some training data. So you have some events which are known to be money laundering, and the majority of transactions are not. And then you do some machine learning to try to detect the pattern. How can I, in the future, what is the signature pattern for money laundering. And you have two different paths. One is you can export your graph data into a traditional machine learning system, or you can keep it within the graph and apply some graph-specific approaches to detect patterns. And we are not proposing either or. We think both are good approaches. This is an important enough problem, and fraud in general is an important enough problem and complex that usually you need multiple approaches. So we would recommend that people do both. So we're going to take a look in the next slide. I'll talk about sort of a graph-specific approach. So once you've detected the fraud, then you can do an investigation, and if it turns out to be a legitimate case, then you can generate a suspicious activity report, and you feed back that information back into your historical data for better training. So here is one approach, one possible approach, a graph-based approach for detecting money laundering. So this is focused on the structuring. Structuring, if you remember, that's when you take your large amount of money and you split it up into multiple smaller transactions. That turns out that actually has a very nice appearance in a graph. It forms a little subgraph of where it starts from one source, it spreads out into different neighboring nodes, but then it eventually merges back into one or a few target nodes. So one approach for this is looking at here in the middle horizontally, you see some gray nodes, and those are the ones where, due to some pattern that the financial institution has learned, maybe due to the amount, maybe due to who was doing this, like or it can be, the person that was doing this, from which or to which account, be the quantity, it can be the frequency. Something caused them to decide that this transaction needs some additional processing. So the graph in general, this is their whole view of transactions. So what you do is you now step both upstream and downstream in the graph. So this is the first step where we're going back. Okay, I have this money. Where did the money come from? And so you see, if you look at, they're starting to pair up now. We started off with 6 transactions, and if you go upstream a level, you now have 6 accounts, and they've now merged into 4 accounts. And on the next slide, if you go upstream one more level, you see it's merged into only 2 accounts. And so you can now see the pattern of structuring, where you started with that $10,000, you split it up into 4,000 and 6,000, and then you split it up again. So there's that splitting up. Okay, that is not illegal. But let's do some downstream analysis now. So now we see, okay, where did that money go? Hey, it's starting to converge again. And if you go one more step down, you see, aha, now my money has come back together. Some of it actually crossed from, we had 2 source nodes, and some of the dollars may have switched from one source node to the other, but we made a significant compression and then sort of spreading out and then bringing back in. And that is a telltale signature of structured money laundering. So what we've looked at here is we've looked at 4 cases. We've looked at phone scam fraud. We've looked at, just money laundering. We have looked at, can you go to the next slide, Gaurav? So we looked at 4 different types. We looked at, let me go to my list here. Phone scam, credit card chargeback, advertising or recommendation fraud, and money laundering. So there are many different types of fraud, But for all of these, what you need is you need the ability to process complex queries, multi-hop deep link queries, and in order to get the best information, the best training data for your predictive analytics, for your machine learning, you need to gather multiple sets of data and large quantities of data. Rich data. Big data refers not just to quantity, but also richness of variety. So you have a distribution so you can see the patterns. If you have all the same data, you're not going to see the pattern. So you need that good cross-section, that good distribution, and of course, quantity. So with TigerGraph, with third generation graph databases, you can do this. First, collecting the data. You can integrate the data, connect it together, connect it in real time. You can then extract the features that you need to analyze. Our query language, G-SQL, is very good. It's very easy to use. You can extract not just the surface features from the vertices, from the nodes and links, but also dig deeper and aggregate and compute to find more secondary features. You can then efficiently feed this information into your machine learning training algorithms. Develop your models, good models based on, again, good rich data, and then take that model and translate it into some checks that you can perform in concert with your transactional behavior. So you performed analytics on a graph, and you're now going to do transactional behavior with fraud detection in your graph. So your graph is both analytical and transactional, and it has to be real time because your transactions are real time, and this is possible with the massive parallel processing that TigerGraph offers. So it can keep up with the speed needs, it can keep up with the scalability needs, and graphs in general also provide the visual explanation. The visual explanation, so first of all this automation, the machine learning cuts down, but it gives you more accurate models, which cuts down on your false positives. So you don't need as many humans to do manual investigation of fraud. You're going to catch more fraud, and you're going to require fewer persons to do manual investigation. But in those cases when you do manual investigation, like in AML, there's usually some step when you have to dig deeper. The visual aspect of graphs make it easier to see what you're doing. TigerGraph has a graphical user interface for running queries visually, so non-experts, people, you don't have to be a programmer, you just have to know your application area and use the graph to very intuitively do your investigation. So TigerGraph offers a end-to-end, well-rounded feature set for enabling more performant, better performing fraud detection than has been possible in the past. And lastly, I think I'll just take a little bit look at the TigerGraph platform itself. So we've been talking about combating fraud, and that's one of the applications that TigerGraph is good for. So let's just take a quick look at the product in general. As I mentioned, we have a graphical user interface. We have our own query language. So on the top edge of this diagram, we show the query language. That's sort of the top edge represents the user interface. We have a query language, we have a graphical user interface, and we have APIs for integrating with other applications. We have a very powerful data importer. G-SQL is not just a query language, but it's also a smart data loader. So you can import data from all sorts of different sources. I said that's an important part, to bring in data from multiple sources and integrate it together. Easily write complex queries and very high performance queries with our GSQL language. Those queries can be turned into REST APIs, and then data is output in JSON format. So there's very easy to use, very standard formats for integrating with any type of other BI tool or other database program that you have. And TigerGraph runs either on premises or on cloud. So that's the technology, little quick summary. I'm going to hand it back to Gaurav to talk about some of our use cases and what your next steps can be. Are you on mute, Gaurav?
Yeah, thank you for that, Victor. We have customers. We have some of the biggest customers, and I just have a few names here. One of the questions that we always get, because people are used to a lot of performance limitations in Graph 1.0 and 2.0. So one of our clients was trying to load 30 terabytes of data into Graph 1.0 solution, and after 15 days they gave up. They said this cannot be done. They loaded up that same data into TigerGraph in 4.5 hours. So typically, customers who have dealt with previous versions of Graph 1.0 or 2.0 have a huge realization that the technology has moved to the next generation and is truly scalable now, as scalable as a relational database. So that's always a surprise, and that's, I just want to mention here, Alipay, one of our largest examples in terms of size. They have 100 billion vertices. Vertices essentially are nodes like payment transactions, customer accounts. All of those represent nodes or vertices in a graph. Over 100 billion of those entities, they have 2 billion real-time updates. When I say updates, I don't mean just querying information. I mean actually really updating the graph. And that's why you'll remember that Victor mentioned transactional or mutable graph. Our graph truly is both operational and analytical at the same time. It's a very unusual thing, and that's why people have a hard time understanding that. It's something that can support both of those use cases. And they are doing 2 billion updates per day. They have over 600 billion relationships between the nodes that are being managed in real time. So that every node in the graph is a computational unit in addition to being a storage unit. So it stores data and it also computes information. So we have things like trust scores being computed for merchants, for devices, for locations. In Alipay, for example, money laundering activities being detected in real time using this. We have several other clients. You can see here, it's a who's who of #1 clients across the spectrum. These are just a handful of our customers. We would love to have conversations with you about your specific needs, because we talked about fraud and money laundering today. Our next webinars will cover topics like e-commerce product recommendation. You'll recognize here #3 customer, Wish, those who have shopped in China, and you'll see that in the United States and Europe as well. Wish sells only through their mobile e-commerce app. They don't have a website. And their entire business is predicated on providing the best personalized recommendation for the customer when they come searching for products. Their entire business is predicated on that, and they have chosen TigerGraph as the foundational technology to do that. Uber, another name that doesn't need any introduction at all. Ride-sharing companies in general are seeing a massive amount of fraud of different forms, and they have been using us to find and curb down that fraud. Last but not the least, Elementum and State Grid of China, the state power grid that supports all of the 1.3, 1.4 billion Chinese consumers. Their entire power grid is modeled as a part of our TigerGraph graph database. So there are multiple use cases. When you go on the website, you'll find those. I would encourage that you look at those in terms of a call to action. So there are 3 things that I want you to look at as you chart your own journey to a more secure, more AML compliant organization. First, please download and read the fraud prevention and AML brief, anti-money laundering brief. It has best practices for you that will help your organization. Next, read the benchmark report, because everybody's going to ask you the same question as you take this back to your organization. How does this compare? What are the other technologies in the market? How does it compare to Graph 1.0 and Graph 2.0 technologies? The answer is very simple. Graph 1.0 cannot handle large volumes of data, can't even load it. Graph 2.0 technologies can load the data, but cannot handle real-time updates or cannot do real-time analysis, and cannot do multi-hop analytics, can't go beyond 2 or 3 hops to do deep link analytics. All of that stuff is documented in the benchmark. Please download the benchmark for your technical audience, the IT part of the organization. And last but not the least, there's nothing better. The proof is in the pudding. There's a link at the bottom of this, the third bullet, which is the test drive. In addition to this test drive, which you can take immediately, you can start playing with the product immediately. You can see every use case in action in there, and it's hosted on Amazon, AWS. You can actually see and download and use TigerGraph with your own data in about 3 weeks. So in 3 weeks, we'll have bring your own data trial announcement. You can get a trial license for us. There's no restriction on the amount of data you can pump in. You can start and run your own proof of concept and feel the power of the TigerGraph technology yourself. So you don't need to take my word for it. You can see it in real time for that. So with that, I did this one chart that I wanted to show you real quick, which is our social. Please follow us on Twitter. Twitter handle is TigerGraphDB. Look at all the videos that we have posted on YouTube for further education of your team. Facebook, if you have an account, and for the business, you can follow us there. Of course, last but not the least, LinkedIn. If you click follow on the LinkedIn, you will get all of the updates that we send out. So with that, let me hand it off to Emily for Q&A.
Okay, thanks everyone. We do have a couple questions here, and the first one is, where were the billions of calls coming from, and how did you get the data? So I think I'm going to ask Gaurav to answer that.
Yeah, great question. Thank you for asking that. All of my friends from Telecom here, a great question. All of you know that we have what are called CDRs, call detail records, that are there. China Mobile has about 500 million phones. Those generate, of course, billions of calls. Their CDR tool is what we get the data from, and then we summarize volume of calls between different accounts, different phone numbers, using the computational capacity. So as I mentioned, we have each of the nodes is storage and a computational unit. So we will populate the edges, the relationship between phones, to say Gaurav called Victor 5 times during last week, and that's the that's the frequency of the calls, and there are details of that call detail record. So we store that information so that we can start to do analysis like, where is the stable group? Is Gaurav calling Victor? Is Victor calling him back? That's a great thing. That means it's a good phone. Gaurav calling Victor. Victor never returns the call. Gaurav called 50 other people, but they never return the call. That's starting to look more suspicious, right? Remember that we talked about the good phone, bad phone. All of that is analyzed using billions of call data. We have capability. We don't have limit in terms of scalability. You can continue to add hardware and scale up TigerGraph. The other thing I wanted to mention, which is different from Graph 1.0 and 2.0 technologies, when you load the data inside, let's say, 10 terabytes of data inside Graph 1.0, it won't take it because it will crash. Graph 2.0, it will take it, but typically it bloats up. So, 10 terabytes of data or 10 gigabytes of data will become 15 gigabytes of data, 12 gigabytes of data. It will grow 20 to 30% because typically the way they store the graph data inside Graph 2.0 is not efficient. What we do is we compress it and we encode it, so that typically we see about 50% savings. So as the data goes, it's loaded up, the data becomes smaller and more efficient. And then we manage it, the performance, with native parallelism. And there's a host of white papers that we have. There's a nice white paper on the TigerGraph website, which you can download or reach out to us, and we'll be happy to share that with you. That actually helps provide that level of scale. There's nothing quite like in the marketplace in terms of proven customers in production with the scale that we have That said, we respect your use cases, your new use cases. We have several of those on the test drive that I mentioned, right at the bottom of the third bullet here. If you have new use cases, there are people who are finding new use cases in healthcare, in pharma, in supply chain, in every single industry that we are working with, and we are excited to partner with you, team up with you, and apply it. Another question here is, how long does it take for your product to develop these queries in GSQL, and how complex it is? So I have a great news for that. Your IT people will be able to start working with GSQL in a day, day and a half. It's about 2 days of training. They'll start coding their own queries. We have our own solution team that works closely with you. In a matter of weeks, you will be up and running with your proof of concept. You can pump your data. Typically, the delay is in terms of getting the data from the client side, not in terms of getting TigerGraph up and running. So you will be up and running in a matter of weeks. If you have a project that you are considering graph technology for, reach out to us. We will provide you with a 2-week license to pump your own data. In about 3 weeks, we'll release that. So you can pump your own data, have TigerGraph on premises for 2 weeks. And then if you want to do more activity with it, such as additional POC, we can talk about that. So this is something that you can experience yourself, and I'll highly recommend that you do. There's a host of things. There's another question here. Thank you. Another great question is about advertising fraud. Typically, pay-per-click frauds, advertising frauds. What we find here, the question was, how do you detect PPC advertising frauds that are coming in from a single source? Typically, we do it based on IP addresses. So if you see that a lot of pay-per-clicks are coming from a group of IP addresses that are all clustered together, then you have something suspicious to look at, and you can drill down further and look at it. Again, because the ability to model the data in terms of an interconnected network or graph, we are able to do that in a relational database. You'll have to connect those dots by doing what are called table joins, and those are expensive computationally, and they're slow. So there's one quote that I love from one of our large clients, chief technology officer. He said, looking at this, I thought this was not possible before. This level of business analysis in real time wasn't feasible before. So I would like you to have that same TigerGraph moment for yourself. So I would encourage all of you to spend some time, learn more about it, learn about our competition, learn about Graph 1.2 and 2.2 as well, and you will see the difference, clear the difference between the scale. There's another question here: what kind of machine learning tools and workflows we can integrate with? There's a host of them. We have customers that are using open source machine learning tools. There are customers who are using proprietary tools. That's a deeper discussion, but you know what? I'll encourage you to contact us. We will show you all the different ways that we are working with our customers and helping them build more efficient solutions. So with that, let me hand it off to Emily.
I think we are done. We're at the top of the hour anyway, so I think if you have any other questions, feel free to reach out to us on our website and look for in your email the deck that we shared with you today and the link to the recording.